In this video, we will learn how to calculate the pH of a mixture containing weak acid and a strong base. There are three different scenarios we are going to look at. In scenario 1, let's assume we mix 100.0 ml of 2.0 molar acetic acid and 100.0 ml of 1.0 molar sodium hydroxide. As you can see, weak acid is acetic acid and strong base is sodium hydroxide. In step 1, we are going to calculate the concentrations of acetic acid and sodium hydroxide when the two solutions are mixed with each other. Each solution dilutes the concentration of the others. First, let us calculate the final concentration of acetic acid. We start with 100 milliliters of acetic acid whose concentration is 2 molar, and we are diluting the acetic acid to a final volume of 200 milliliters. We are supposed to calculate the final concentration. The final concentration is equals to initial concentration times initial volume divided by final volume. That is 2 molar times 100 ml divided by 200 ml. If we do the math, we get the final concentration of acetic acid is equal to 1.0 molar. Next, we will calculate the final concentration of sodium hydroxide after mixing. The calculation is quite similar, and if we do the math, we get the final concentration of sodium hydroxide as 0.5 molar. So, in scenario 1, the concentration of the weak acid after mixing is greater than the concentration of the strong base after mixing. Let us now calculate how to calculate the pH of such a solution. So, after mixing, the solution contains 1.0 molar acetic acid and 0.5 molar sodium hydroxide. Acetic acid is a weak acid and it dissociates in water according to the following equation. Acetic acid reacts with water to form acetate ion and H+ ion. Since this is a weak acid, at equilibrium, a majority of acetic acid molecules stay undissociated. Only a fraction of molecules break to give acetate ion and H+ ion. Therefore, acetic acid is major species and acetate ion, which is the conjugate base of acetic acid, is minor species. Let us now see what happens with sodium hydroxide. Sodium hydroxide reacts with water to form Na+ and OH- ions. And sodium hydroxide is a strong base, which means it dissociates 100%. Therefore, at equilibrium, we do not have any undissociated sodium hydroxide in the solution, and the major species is Na+ and OH-. The next step is to check if there are any incompatible species present in the solution. For example, a weak acid acetic acid and a strong base OH- cannot coexist in the solution. They always react with each other. The reaction is as follows. Acetic acid reacts with hydroxide ion to form acetate ion and water. If we carefully look at this equation, this is an exact reverse reaction of base dissociation of acetate ion. The Kb value for the base dissociation of acetate ion is extremely small. Therefore, the K value for the current equation would be inverse of this extremely small value, which would be an extremely large value, which means this reaction is a strong reaction and it goes to completion towards products. In other words, this is a limiting reagent type problem. Now let us set up an ice chart. At the beginning, we have 1 molar acetic acid, half a molar OH minus ion, a very negligible quantity of acetate ion, and we do not have to worry about water. Since acetic acid and OH minus reacts in 1:1 ratio, OH minus is the limiting reactant and it would be completely consumed. Therefore, the change for acetic acid is half a molar, for hydroxide ion is also half a molar, and half molar acetate ion is formed, and water we do not have to worry about it. At equilibrium, we have half molar acetic acid, 0 molar OH minus ion, and half a molar acetate ion. Acetic acid is a weak acid and acetate ion is its conjugate base, which is also a weak base. And after all the reactions happened and at equilibrium, we have appreciable amounts of acetic acid, which is a weak acid, and acetate ion, which is a weak base. Each of these species, that is acetic acid and acetate ion, can individually affect the pH of water. And we have learned earlier how to calculate the pH of the solution containing acetic acid by itself or acetate ion by itself as major species. But in this solution, we have both acetic acid and acetate ion as major species. Let us now learn how to calculate the pH of a solution that contains a significant amount of a weak acid and its conjugate base. We know that the acetic acid reacts with water to form acetate ion and H+. If we write down the equilibrium constant expression for this reaction, Ka is equals to concentration of acetate ion times concentration of H+ divided by the concentration of acetic acid. Let us apply logarithm on both sides. Log Ka is equals to log of concentration of acetate times concentration of H+ divided by concentration of acetic acid. We know that log A times B can be written as log A plus log B. I'll use this formula to manipulate this equation. Log Ka is equals to log of concentration of acetate ion divided by concentration of acetic acid plus log of concentration of H+. If I multiply both sides with -1, I will get negative log Ka is equals to negative log acetate ion concentration divided by acetic acid concentration minus log H+. The negative log of H+ ion concentration can be written as pH, and in the same way, the negative log of Ka can be called as pKa. And then we have negative log acetate ion concentration divided by acetic acid concentration. If we isolate the pH term in the earlier equation, we get pH is equals to pKa plus log concentration of acetate ion divided by concentration of acetic acid. For a generic weak acid reacting with water to form its conjugate base and H+, and governed by an equilibrium constant Ka, the pH can be written as pKa plus log concentration of A minus divided by concentration of HA. That is, concentration of the conjugate base divided by the concentration of weak acid. This is called as Henderson-Hasselbalch equation. It is a very famous equation using which we can calculate the pH of a solution in which we have appreciable quantities of a weak acid and its conjugate base. Now, let us get back to our problem. After the strong base OH minus reacted with acetic acid, at the end we have appreciable quantities of acetic acid and acetate ion, that is, a weak acid and its conjugate base. We know that we can use Henderson and Hasselbalch equation to calculate the pH of such a solution. pH is equals to pKa plus log of acetate ion concentration divided by acetic acid concentration. The pKa of acetic acid at 25 degrees Celsius is a constant and it would be provided to you. Or you can calculate pKa by taking negative logarithm of Ka value for acetic acid. The pKa for acetic acid is 4.75 plus the log of concentration of acetate ion, which is 0.5 molar, divided by concentration of acetic acid, that is 0.5 molar. If we do the math, we get pH is equals to 4.75. So this is how we calculate the pH of a mixture containing a weak acid and a strong base.